Okay, let's do this one. So power series. Power series is on the exam Friday. So let's look at this one. So what is a power series? Power series is, it's a series, but then it's also a function of x, right? So x is allowed to vary, right? Variables vary. So x can vary, and every time x changes, you get a different series, right? So we want to figure out which values of x the series converges, and which values of x it doesn't. So how do we do that? With the ratio test, right? So we're going to look at the limit as, say, I goes to infinity of -1 to the I plus 1, x minus 6 to the I plus 1, over 18 to the I plus 1, I plus 1 to the 5th. Times? Yeah, this, I'm thinking this isn't great up here. This is going in the wrong direction. 18 to the I to the 5th, -1 to the I, x minus 6 to the I. Okay, so we're going to gather like things together and simplify. So it looks like I'm going to have 1 x minus 6 in the top, right? The -1 is nothing because we're going to do absolute values. So then we're going to have 1 x minus 6 in the top. And what, 1/18 in the bottom? Anything else? And then the limit as, so I to the 5th over I plus 1 to the 5th. Do I have that simplified correctly? So what is this limit? As I gets really big, what do we have? X minus 6 all over 18. That is an easy limit, goes to 1, right? I to the 5th over basically I to the 5th when I gets large. Okay, so then in order for this thing to converge, we know in the ratio test, whatever we get for the limit has to be less than 1, right? What is this thing, essentially, in the ratio test? What is that thing, essentially? Remember what the ratio test is about? Is it becoming a geometric series, right? Is it becoming a geometric series? So this is like what? This thing is like the value of r, right? In a geometric series. And if that thing, as I gets big, if that r falls in the range for a convergent geometric series, -1 to 1, then the given series will converge. So this is like the r, and we know for geometric series r has to be between 1 and -1. But now this is a function of x. We got to figure out which values of x make that r between 1 and -1. So we have x minus 6 over 18 has to be between -1 and 1. So we got to figure out what to solve for x, right? What values of x make this true? What values of x make this true? First step, multiply by 18. And then add 6. So -18 plus 6 is -12. 18 plus 6 is 24. So we know for sure if x is between -12 and 24, that original series will converge, right? Because if that's true, if x is between -12 and 24, then this thing will become like a geometric series where its r is turning into a value between -1 and 1 if x is between -12 and 24. So we would need to check -12 and 24. If we actually wanted the interval of convergence, meaning we want to figure out exactly what x makes this thing converge, then we need to check -12 and 24 separately, right? So -12 and 24 makes the ratio test equal to 1. That's our inconclusive, right? So we'd plug negative 12 in for x, and we'd have a series, and we would check it. Does it make it converge or not? If it does, then we include negative 12 in the set. If it doesn't make, if negative 12 in for x does not make that converge, then we would not include it. Same with 24. But this question just asked for the radius. So the radius, so you think of this as like the diameter, right? Like this, like the whole interval is like the diameter of a circle, and then the radius would be half of that. So this whole, so basically we're going from negative 12 to 24, which has a diameter of what? 36. So the radius would be 18, half of that. Any questions? So we won't take the time. We got more to do, so we won't take the time. But again, if we wanted the interval of convergence, meaning we need to determine all values of x that make this thing converge, we would plug the negative 12 in for x. And then what would we get? We would get negative 18 over n, which is negative 1 to the n, times another negative 1 to the n. If I plug in negative 12, I'm going to this will all simplify to just 1 over n to the 5th. Convergent or not? 1 over n to the 5th. Convergent p-series, right? So we would include, so I did that fast, but if you were to plug in negative 12 and simplify this, you would just get, all this would go away. If you plug in 24, you get negative 1 to the n, negative 1 to the n over n to the 5th, because those two go away. Convergent? Yes. So in this case, both endpoints still make this thing converge. So we would include both negative 12 and 24 in our values of x that make it converge. Questions on this example? Okay, so today we're going to start Taylor and Maclaurin series. So Taylor and Maclaurin series per se will not be on the exam. But everything we do today is going to involve all the stuff we've been learning. So there's lots of great kind of review and study for the exam, the principles and the things that we use all along today. But Taylor and Maclaurin per se won't be on the exam. So what does the exam cover? It covers everything since spring break. Everything since spring break, okay? Which started with Dr. Thompson. So, and there's an outline of that on Blackboard. Tomorrow night at like 6 or 7, I can't remember, I set it for 6 or 7 p.m. For sure after 7 p.m., all the answers to those book practice problems that I posted will be also posted there in that post. Any questions about the exam? If you haven't replied to my email about conflicts with Friday morning, please do that today so we can set up time for you to take the exam. Yes, sir? So it's since the spring break, and it's all outlined on Blackboard. It's just all that sums and series and Dr. Thompson stuff. Other questions? Okay. So today, Taylor and Maclaurin series. So arguably today's lecture is kind of maybe the most important thing. Like this last topic is kind of like the whole reason for all this stuff. So arguably the most important. Okay, and there's a lot to keep track of. Like, so we have to really know what we've done so far, and really kind of pay attention as we're building this, because there's lots of details, and I would say it's a slight degree more difficult than what we've done so far, just because of all the things you have to attend to and keep track of. All right, so what a Taylor and Maclaurin series does is allows for writing any function we want as an equivalent power series. And what kind of function, again, was a power series in general? What did we say was a power series?
C sub I times X sub I, or X sub
What was it? Yeah, like a polynomial with an infinite number of terms. That's what a power series is. You just keep adding terms with a higher and higher power, right? Okay, so basically, what we want to do is we want to take like a non-polynomial, like an exponential or a trigonometric function, and say, how can we write that as a polynomial? Okay, so, or in other words, how can we write it as a power series? Why would we want to do that? Well, because polynomials are really easy to work with. Like when you think about derivative and antiderivative, they're just very user-friendly, right? They're just all based on arithmetic. Just the power of a value and then times the coefficient. Exponential and trigonometric functions are kind of a little more elusive, right? They're not so, they're based on definitions that are not just pure arithmetic like polynomials are. So if we've got like an exponential or a trig function, there's advantages to rewriting it as a polynomial because of how easy polynomials are to work with. Okay. So a Taylor-Maclaurin series is a power series. Okay. A Taylor polynomial is not an infinite series, but has this form. Okay, and then we say it's centered at A. Centered at A. So really all this is just a standard polynomial, degree n, and then we just subtract A from all the x values. And what does that do to the graph? What does that do to the graph if you subtract A from all the x values? Do you remember? Shifts it to the right. It'll just shift it to the right. So this is just, all this is the formula for a polynomial of degree n, shifted to the right by A units. So that may look a little scary when I first put it up, but it's not bad, right? We know for every term we have a coefficient. I'm calling those C. And then starting from power n, we have all the powers down to 1 and then a constant term, C sub naught, or C naught. So this is just a standard form of polynomial shifted over A units so that it's like we're centering at some x value, which we call A. Okay? So here's what we want to do. So given a function f that's not a polynomial, we want to figure out what are those coefficients that would make this polynomial approximate the function f near A or at A and around A. So we're gonna do sine of 1/2 x. That's what we're gonna start with, okay? After we work through this. So here I've got sine of 1/2 x. I want to try to figure out, and I want to center, say, at x equals 1. So what would be the coefficients of this polynomial that would approximate sine of 1/2 x around in the neighborhood of x equals 1? That's what we're after. So how would we pick those coefficients that would make that polynomial do that? Approximate or try to replicate this function f, like sine of 1/2 x. Okay? So that's what we're after. Okay, we're after the coefficients. The coefficients that would make the polynomial approximate a function f that we're interested in. Okay, so here's what we're going to do. We're going to start with saying, looking at that formula, what is the value of that polynomial at A? So if I were just to plug A into that approximating polynomial, what would I get?
Sine. 0.
Like it's 0?
C sub 0?
Yeah, I would just get the constant term, right? I would just get C naught. Okay? So if this polynomial t is going to approximate f, right? What would we want C naught to be? Right? What would we want C naught to be? So this is, if we want this to be approximating what f is near A, then what would we want C naught to be? So when we plug a into our approximating polynomial, if we just get a number, what number would we want it to be? Not a. F of a, right? We would want that to be f of a so that we get the same thing, right? We get the same thing in the polynomial that we do in the function, right? So what we're going to do for C naught, that one's easy. We're just going to say that's going to be f of a. Let's do blue. That should make sense because so f of a is what we get when we plug a into the actual function. So what should we get when we plug a into our approximating function? We should get f of a. Make sense? Okay. All right. So now the next thing we're going to do is we're going to take the derivative of this, the derivative of our polynomial. So we're going to use the power rule, right? So can you imagine? It's going to be n times c of n x minus a to the n minus 1. And then n minus 1 times that coefficient x minus a to the n minus 2. And we're going to do that the whole way. So we're going to take the derivative, and that's what we get. Just the power rule on all those terms. And then we're going to think about, okay, first of all, so what would the first derivative at a equal to now? So I've found the first derivative. What would the first derivative at a equal? You see that would be 1c1, right? All those terms will cancel out to 0, and I'll have 1c1. Okay, so what do we want 1c1 to equal? So if we want the first derivative of our approximating function of a to be what? What do we want that to be? F prime of a, right? So we want this thing to be f prime of a, or t a. So that would mean that c1 would also be f prime of a. Okay, so far we have our approximating polynomial will give us, if we plug in a, it'll give us f of a. And if we take the derivative of it and plug in a, it'll give us f prime of a. Okay, so that's exactly what we want it to do, right? So it's giving us the actual function value, and it's giving us the first derivative at a correctly by making c1 be that and c naught be that. It gives us the right function value. This approximating polynomial gives us the right function value at a, and it gives us the right first derivative at a. Does it make sense? Okay, next one. So now I'm going to take the derivative again. I'm going to take the derivative of, or take the second derivative, and I get this thing. And so what will the second derivative at a equal? What will t double prime of a equal now? 2c2, okay? And so when I plug in a into the polynomial, into its second derivative, I would want to get what value? What do I want to get? F double prime of a, right? That's what I want. So what does that make C2? What should C2 be so that if I get the right second derivative at a? What does C2 need to be? F double prime of a over 2 times 1, right? So I'm going to make C2 F double prime of a over 2 times 1. And what will happen if I do that? If I make C2 that, then when I plug a into the second derivative, I'm going to get the right second derivative. I'm going to get F double prime of a. Okay? And we can go on like this. Here's the third derivative. Here's the third derivative taken at a. And so what are we going to make C3 so that we get the right third derivative at a? We're going to make it F triple prime at a over, and what is this? So I got 2 times 1, then 3 times 2 times 1. 3 factorial, right? And that's 2 factorial. And could we say this is divided by 1 factorial? And this is divided by 0 factorial is 1, right? So what are we doing? We're picking these constants, these green constants on the approximating polynomial to force what? The actual function value at a to be correct, the first derivative at a to be correct, the second derivative at a to be correct, and so on. Okay? And so all the way until we get to the nth derivative is going to give us, if we at a, evaluated a, will give us n factorial Cn, which means that, what should we make Cn? Nth derivative, right, the nth derivative at a over n factorial. So we're picking these coefficients in such a way so that that approximating polynomial gives us the right function value at a, gives us the right first derivative at a, gives us the right second derivative at a, gives us the right third derivative. If we pick the coefficients to be this, then we get like everything correct at a, right at a. We get the function value right, we get the first derivative correct, we get the second derivative correct, etc. Okay, so now let's look at that example, the sine of 1/2, and see what's going on here. Okay, so yeah. Okay, so here it is. So our function that we're interested in approximating with Taylor polynomials is sine of 1/2 x, or sine of 0.5x. All right, so I want you to find the Taylor coefficients C0 to C4 based on what we just did, and then the Taylor polynomials T0 to T4. So I showed you the Taylor polynomial for just a general case n degree. All right, so you can have a Taylor polynomial that's just the 0 degree, and then you can have the first degree, and then the second degree, etc. So see how, I'm going to take attendance, see how you do on this. So you're going to find, for this function centered at 1, so a is 1, and the function is 0.5x, find C0, C1, C2, C3, and C4, and then see if you can write the Taylor polynomials. And it might be easier if you write this one first. So go backwards. Write T4 first, and then ask what would T3 be, and what would T2 be, and T1, etc. Because T4 looks the most like the one that we had. All right? Okay, what is C0? What do we find? What do we say C0 should be? Just f of a, right? So you should have C0 as f of a, right? That's what we said. In order, if you plug a into this approximating polynomial, you'll just get C0. And we want that to be f of a. We want it to approximate the right function value. C1. What is C1? So it's the first derivative evaluated at a over 1 factorial. Did anyone get that? Right? So it's the first derivative evaluated at a over 1 factorial. That's what we said, right? But now we've got the function. We have an actual function now, sine of 1/2 a. Yeah?
Don't you add C0?
No, that's the polynomial. You're thinking of the first polynomial. I'm just going to the coefficients. Just doing the coefficients. Yeah, you're right, though. I mean, that's what T1 would be with the x minus a thing. Yeah. Okay? So C2 would be what? What would we say? It's going to be the second derivative evaluated at a divided by 2 factorial. That's that. Did I lose you? Yeah.
To get actual values for these
Yes. Yeah. So yeah, in our case, a is 1. So if you just had 0.5 cosine of 0.5 over 1 factorial, that was right too. That's right too. And if you have negative 0.5 squared times sine of 0.5 over 2 factorial, that's correct because a is 1. Our a is 1. I'm just, for my file, I want to, in my GC file, I can just go up and change a to something else and it makes everything work. Okay, so I'm just keeping it as a for my file. But for our example, a is 1. So what is the third coefficient? So it's going to be the third derivative evaluated at a over 3 factorial. And so that's just what? Cosine of 0.5a now times 3.5s, and we still have the negative. Okay, have I lost you? If I lost you, ask. Is it good? All right, and then finally C4. We don't want to go much further than this. Again, one more derivative. So the derivative of negative cosine is positive sine, and by now we've accumulated 0.5s, right? 4.5s in the chain rule, right? We've done the chain rule 4 times now. Over 4 factorial. So here are those coefficients. And yes, for our example, a equals 1. So you could just, all those a's could be gone and you'd have the right answers, right? Yeah? I'm sorry? I'm sorry, I don't understand your question. One more time?
Are we not multiplying C3 by 1 by 2 because 1 by 2 factorial comes from C2
Well, it goes back to the previous, what we did on the previous slide. So we had that t, our polynomial t, the third derivative of evaluated at a, we came up with was 3 factorial times C3. Remember that? So we're asking, what should we make C3 so that if we plug a into the third derivative, we get the third derivative at a in the actual function. So we want this thing to be the third derivative at a, so that our approximating polynomial gives us the right third derivative at a. So then what does that make C3 equal to? So what would I choose C3 to be in order that this will give us this, right? So that the approximating polynomial will give us the actual third derivative at a correctly. So I'm basically solving for C3. What should I make it? Third derivative at a, what? Divided by 3 factorial. So I'm solving this for C3. I'm asking what should we make the value of C3 so that if I plug a into the third derivative of our approximating polynomial, I get the third derivative of the function at that value of a. So is it better? So that's why I'm doing the third derivative evaluated a divided by 3 factorial. Okay, so now what about the polynomial? Let's start with, how about T4 first? So what would the fourth polynomial be, approximating polynomial for f? Anyone think they got it? What would it be? So we did just a generic version, Tn, right? Tn goes all the way up to x minus a to what power? N. So this is going to go have all the terms up to x minus a to the fourth. I'm actually going to write it backwards. So we're going to write it backwards from what we had before. So what will the first thing that we'll have be? All right, so I'm going to make that last. Like I'm going to switch the order. So x minus 1 to the fourth times c sub 4. That's it, right? And now we know what c sub 4 is. C sub 4 is all this, right? And what else will we have in the fourth Taylor polynomial? What's the next one we'll have? C3 times x minus 1 to the third. So this is just rewriting what I had for Tn of x, but now we actually have a highest power, right? So n was just a generic highest power. For the T4 polynomial, 4 is the highest power. Okay? Plus C sub 2, x minus 1 squared, plus C1, x minus 1 to the first, plus C naught. So what is this? This is a polynomial, right? And it approximates, this polynomial will approximate sine of 1/2 x at x equals 1 for up to how many derivatives correct? How many derivatives will it get correct? It'll get the function value correct. This, because we have C1, it'll get the first derivative correct, and then the second derivative, third derivative, and it'll get all the way up to the fourth derivative correct. But then after that, after that it won't be correct because it's just only approximating up to the fourth derivative of sine of 1/2 x. Does it make sense? I know this is kind of trickier. This is the best I got. I'm doing the best I can. All right, so then what would, I shouldn't erase that. What would, shoot. Okay, so what is how about the 0th Taylor polynomial? Let's start from that direction. So what is T0 then? Good, just C0, right? So what does that get correct? All that gets correct is the function value. In fact, that is a constant function. So that's just going to give us a straight horizontal line for all values of x. And the only thing it gets right is the actual function value at 1. What about T1x? What will that? C0 plus C1 x minus a. That will get the right function value, but also get what? It'll get the right slope, right? It'll get the right rate of change. And so what will that graph be compared to sine of 1/2 x? What will that be? That will be the graph of the... Let's go through all, and then I'm going to show you. All right, so then second, the T2 has C0, C1, and C2, and then T3, and then T4, the one we already wrote out. All right, so I'm going to show you these compared to the function. So the red graph is our graph that we're trying to approximate. Right now I'm showing you the 0th Taylor polynomial, T0. Right? What does it get correct? The only thing it gets correct is the function, it gets the right function value at 1, right there. But nothing else about that blue graph is correct in terms of trying to approximate sine of 1/2. Okay? So then what will, when I show you T1 of x, what will that look like? What will the blue graph become if I show you T1 of x? Good. Right, the tangent line, because the tangent line gets the function value correct and also the first derivative correct. And actually now there's a little kind of neighborhood around 1 where it's doing a really good job of approximating the function. You see that? So now it's kind of all black there, right? You see that for a little ways for an interval of x? All you see is kind of purple because that tangent line is doing a pretty good job of approximating sine of 1/2 x at 1. So what will we get? What will T2x be? What kind of graph will that be? A parabola that does an even better job approximating the function at x equals 1. So that's our second degree Taylor polynomial for sine of 1/2 x at 1, centered at 1. And so then every time we add another term, so here's our third degree Taylor polynomial. And you see there's lots of purple now, right? Away from 1. All this stuff that's purple away from 1 is all where that approximating polynomial is doing a really good job reproducing your original function. And the last one we did was quartic, right? So here's if I zoom out, you'll see that that's a quartic. So it has another loop to it. But this looks really good all the way from, say, -1 to 3. All the way from -1 to 3. This is doing a really good job now of reproducing the original function. See that? Why? Because it gets the function value right, it gets the first derivative right at 1, it gets the second derivative right at 1, and the third and the fourth derivative. It gets all those correct at t equals 1. So this is right now, I'm graphing this one right here. The blue is t4. So looking at these functions, what does this remind you of? Looking at that progression of functions should remind you of something that we've been doing. What does that remind you of? T0x, T1x, T2x. What's happening as we keep going to the next one? Okay, so you got a sequence of partial sums, right? Isn't this a sequence of partial sums? We keep adding one more each time. All right, so what's the limit of the sequence of this function, right? So what's the limit of sequence of partial sums? What's the limit of a sequence of partial sums? The same as value of the infinite series. See if you can write an expression that equals, that's the same as the limit of this sequence of partial sums. Could you do it? Could you write an expression that's the same as the limit of this sequence of partial sums? In other words, it would be something like t what? Can you write something that would be like this? That would be the limit of that sequence. If you just kept going and going and going, T5, T6, T7, T8, all the way, just kept taking the next one and the next one and the next one. What would the limit of that sequence be? See if we can apply what we've learned. Anybody want to give it a shot? Yeah, Andrew. What's that? Yes, right, good. So that's one way to say it. So the limit of that sequence would be the actual function. Good. Now, but I want to write that. Okay, so how can I write that? How can I write the limit of the sequence of partial sums? Sum? Sum as, let's do our index first here. Sorry, I didn't hear you. Okay, you want to use n? What do you want to use? 0 to infinity, okay. Cn.
X minus a to the n.
What's that? So for our example, a was 1, right? For our example, a was 1, but we'll just leave it generically as a, right? So yes, so if you have x minus 1, that's correct for this one. Okay, we'll just leave it as x minus a. Okay, and what is Cn? We know what Cn is. The nth coefficient is, what is it? The nth derivative at a over n factorial. So what is this? This is like the Taylor polynomial with all the terms, like with an infinite number of terms. And so this is like the sum of the series, or the limit of that sequence of Taylor polynomials. You just keep adding terms. You just keep taking higher and higher derivatives and adding terms with higher and higher power. Okay? So this right here is called, these are Taylor polynomials. These approximate. This is called the Taylor series. Right? Because it's the sum of all of the terms, right? Or it's the limit of that sequence of polynomials. So that's the Taylor series. And like he said, it equals f of x. So if we kept taking higher and higher powers, we keep doing better and better, and this neighborhood around 1, where the blue graph is doing a good job, will just keep expanding and expanding out further and further away, and eventually, if we could add all infinitely many terms together, the blue graph would be the red graph in the end. Yeah.
How do we know how big the neighborhood is?
Right. So that's the interval of convergence. So once we find a Taylor series, we're going to analyze it with the ratio test, just like we've been doing, like a power series, just like your homework for today, and that'll tell us where it converges. So this particular one converges for all x. This will converge. The blue graph will just keep wrapping itself on the red one as you move out from one. And then if you somehow were able to add all infinitely many terms, the blue graph would be the whole red graph everywhere. All right, so let's just summarize here. All right, again, what are we doing? Taylor series. We're trying to write any function as an equivalent power series. And so this is the Taylor series, centered about x equals a. We know those coefficients. We always take the nth derivative at a divided by n factorial. That's the coefficient. And then to get the polynomial, we'll multiply each of those coefficients by x minus a to the n. And then we're just going to sum all those up and get this. Again, this is a power series. It's a polynomial with infinitely many terms. That's doing what? That's replicating f, right? That's replicating f as a polynomial function. So this is how we would write it out the long way. And this is exactly what we came up with for those polynomials. So the 0th polynomial is just the first term. The first polynomial gives us the tangent line. It's the first two terms. The second degree polynomial is a parabola. It's like a tangent parabola. The third degree polynomial is like a cubic approximation at a, etc. The series is the sum of all of them. Okay, so last thing. A Maclaurin series then is actually easier, right? Because the center a equals 0. So we center, a Maclaurin series is a particular example of a Taylor series when we center it at 0. So it makes it easier, way easier. So I want you to write the general form for a Maclaurin series, right? So write this. What would this be for if we're going to center at A, right? And that's all a Maclaurin series is. So write it out. Did you get that? So this is the Maclaurin series now. So you're going to take all the derivatives at 0, and then it just becomes x to the n, because a is 0. So it just becomes the nth derivative at 0 times x to the n over n factorial. So like Maclaurin series is like the easiest case of all the Taylor series, because you're going to center right at x equals 0.